So shall we wait for some time or we are starting now?
Yeah, we can start actually. Maybe 1 or 2 minutes. Otherwise, we can start.
Yeah, live stream is on.
Yeah, okay. So let's start. Sudarshan?
Yeah.
Yeah, okay. So welcome everyone. We are glad to have Sudarshan Gurjar continuing his talk on Riemann-Roch Theorem for compact Riemann surfaces. So over to you, Sudarshan.
Yeah, thanks again. So this is a second talk that I'm giving, continuation of the talk I gave last week on divisors and line bundles. So Riemann-Roch theorem is the broad topic. So let me just spend 2 minutes recalling the last lecture. So in the last lecture, we discussed the correspondence between divisors and line bundles. To quickly recall this correspondence, given a divisor, I'm always on a compact Riemann surface, by the way. So now given a divisor D, which is summation AI Pi, we associate a line bundle LD described using an open covering and transition functions by taking the open covering consisting of small coordinate neighborhoods Ui, Zi around each point Pi in the support, along with the open set U, which is given by x minus the complement of the support. X minus the support. So small neighborhoods around each point Pi and complement of all the Pi's. All they together form an open covering of X. And on the intersection of U with Ui, define the transition functions Zi going to Zi to the power Ai, going from the basis over U to the basis over Ui. So this defines a collection of transition functions and therefore defines the data of a holomorphic line bundle. As I said, co-cycle condition is automatic here because no three open sets intersect. So this data of open coverings and transition functions defines a holomorphic line bundle. In the reverse direction, given a holomorphic line bundle L, choose a meromorphic section S of L and consider the divisor of its zeros and poles, counting multiplicity, always zeros with positive sign and poles with negative sign. And the image of this divisor in the class group, divisors modulo principal divisors, is well defined. So if you choose a different meromorphic section, the divisor gets disturbed by a principal divisor. Right? And these two correspondences are inverses of each other, which therefore give an isomorphism from the divisor class group to the Picard group. Okay. Now, I did not discuss many examples last time because there wasn't enough time, but let me discuss sort of two important examples in this lecture. So one is on CP1, the Riemann sphere, there exists a tautological line bundle denoted O minus 1, and we define it as follows. So now I'm describing a very specific holomorphic line bundle. So thinking of CP1 as the space of lines in C2 through the origin, we define the total space of this line bundle as the collection of pairs P comma V, so that V belongs to the one-dimensional subspace spanned by P. So all pairs P comma V, so that V is a vector in that one-dimensional subspace of C2 that P defines. So there exists an obvious projection map to the base, sending a pair P comma V to the point P. Thus, over any point P in CP1, we have attached the one-dimensional subspace of C2, which the point P corresponds to. Now, one wants to check that this is a holomorphic line bundle. So one can check that this projection satisfies local triviality. So choose Z1 and Z2 are the coordinates on C2. Now on the open subset U defined by the set of points where Z1 is not 0, define a trivialization from pi inverse of U to U cross C by send a point Z1, Z2. Points in CP1 look like pairs of points Z1, Z2, where Z1, Z2 is equivalent to lambda Z1 comma lambda Z2. So an equivalence class is denoted bracket Z1, Z2. So Z1, Z2 comma a vector V1, V2 goes to the vector V2. So this is how you define the trivialization on pi inverse U, and on the open set V consisting of points Z1, Z2 with Z2 not equal to 0, define pi inverse V to V cross C by Z1, Z2, comma a vector V1, V2 goes to the vector V1. I mean, I should really say P comma V1 and P comma V2 and P comma V1. It's going to U cross C and V cross C. So it's P cross V2 and P cross V1. P comma V1. The transition functions are defined on the intersection U intersection V to C star. When you have an open, the transition functions will go from the intersection to C star. And now U intersection V is just C star because both U and V are just P1, CP1 minus 1 point each, and the intersection of them is just the C star. And now it's easy to check that with respect to the usual coordinate Z on C star, the transition function GUV to C star is given by Z goes to Z inverse. So with respect to this choice of trivialization, the transition function on the U intersection V, which is just C star, this is given by Z goes to Z inverse. So therefore, this defines a holomorphic line bundle on CP1. Yeah, I hope more importantly, the construction of the line bundle is clear. Checking local triviality is not difficult. Yeah, for every point on CP1, you are attaching that one-dimensional vector space which this point in CP1 corresponds to. That's all. And then its local triviality is not difficult to check. Okay, so yeah. So this is a concrete example of a line bundle, and a similar picture carries over to CPN in general. You will have to cover CPN by n plus 1 open sets where each of those homogeneous coordinates is non-zero, where each open set UI corresponds to the open set of points where the ith homogeneous coordinate is non-zero. On that you can trivialize this line bundle, and now the transition functions will be defined on all possible intersections. So this picture goes through almost identically to CPN as well. Okay, now with notation as before, notice that, okay, so I should say that, remember that for a divisor D, we call the associated line bundle L suffix D, right? This was a notation from last lecture, given a third line, we associate a line bundle LD. Okay, so now with notation as before, notice that LD comes equipped with a natural section S suffix D defined by the transition functions Zi to the power AI on UI and identically 1 on U with respect to the chosen trivialization. So I mentioned in the last lecture that every holomorphic line bundle comes equipped with a always admits a meromorphic section, whether or not it admits a holomorphic section. Now, if you have a divisor D and you take a line bundle LD, it comes equipped with a very natural meromorphic section. This section SD is meromorphic, and you define it this way. So how do I define a meromorphic section? If you describe the line bundle using an open covering and transition functions on each of those open subsets, on each of those open sets, I should define meromorphic functions, and those meromorphic functions should transform according to the transition functions. Gij times transition function on Uj should be the meromorphic function on Ui. That's the kind that if I define my meromorphic functions in this way, which are sort of compatible with the transition functions, then I would have defined a global meromorphic section of the line bundle. So explicitly, I'm now defining an explicit or a very concrete meromorphic section SD on this line bundle LD, and defining it this way, define the functions to be Zi to the power AI on UI and identically 1 on U, which is the complement of all the PIs with respect to the chosen trivialization. Now it's clear that the divisor of S suffix D is exactly D. Yeah, so this is a meromorphic section of LD whose divisor is exactly D. Now such a divisor is unique up to scaling. For if S prime D is another meromorphic section whose divisor is exactly D, then SD upon SD prime is a function, not divisor, is a function, is a function with no zeros and poles, and hence defines a nowhere vanishing holomorphic function on X, and is therefore constant. So therefore, this meromorphic section SD is unique up to scaling by a non-zero constant. So now we wish to understand the sheaf of sections of L suffix D explicitly. We begin by making a definition. So for any divisor D as above, define a sheaf OD of U. This is all meromorphic functions F on U, so that the divisor of F restricted to U plus the divisor D restricted to U is greater than or equal to 0. So this is the notation for divisor of F. So divisor of F plus D. Now this defines the divisor on U. This should be an effective divisor. All coefficients should be positive. So in some sense, whatever negative signs occur in D, those should be cancelled out by the zeros of F. That is this condition, divisor of F. And now when U is equal to X, we also denote OD of X by this vector space H upper naught of X comma L. This is the what's called the zeroth cohomology group with coefficients in L. And this is just an alternate notation for OD of X, the global sections of this sheaf. So just to understand that, just to make sure that we understand this definition, let's take a simple example. For example, if D is the divisor P plus Q minus 2R for 3 distinct points P, Q, R on X, then OD of X is all meromorphic functions F on X, so that F has a pole of order at most 1 at P and Q and a 0 of order at least 2 at R. Yeah. So P and Q, remember, occur with positive sign 1 with coefficient 1. So you can at most have a pole of order 1 at P and Q, so that when you sum up the when you add D to the when you add the divisor of F to D, the coefficient of P still stays non-negative. If you, for example, if you have a pole of order 2 at P, then when you take D plus the divisor of F, you will have a negative coefficient for P. So that's not allowed. So you can have a pole of order at most 1 at P and Q, and you are allowed to, and you must have a 0 of order at least 2 at the point R, because you need to cancel the minus 2. Yeah. To compensate for this negative sign minus 2, you need to have a 0 of order at least 2, so that when you take D plus divisor of F, you get an effective divisor. So maybe let me pause at this point and ask if there are any questions.
Did you tell what sheaf is?
Sorry?
Did you tell what sheaf is?
Sheaf.
Sheaf. Well, it's a long definition, so maybe let me not define what a sheaf is, but just keep this.
Some examples, basic naive examples.
Naive example, for every open set, you can consider the abelian group of all holomorphic functions on U. That's a sheaf. And now if V is a smaller open set contained in U, you can restrict the holomorphic function on U to a holomorphic function on U, on V. So there is this restriction map from the group that you are defined on U to the group that you are defined on V. So this kind of thing is basically a sheaf, roughly speaking. There are some more conditions. So for every open set, you are
we know all the meromorphic functions on the Riemann sphere.
Yeah.
So for the Riemann sphere, yeah, can you illustrate? Yeah, some of your examples.
Well, actually, I made this remark in the last lecture. So
Yes, you did. Yes.
So basically, the degree zero divisors on CP1 are all principal divisors. Every degree zero divisor comes is the divisor of a meromorphic function. And
Yeah,
I had
but
taken
what
it.
is your LD and
Right. So actually, I have some comment on this later. So maybe let me just postpone it for a moment. I'm going to come back to this point.
all right.
Okay, go ahead.
Yeah. Now it's easy to see that the holomorphic sections of LD over an open set U can be identified with OD of U by F goes to F times SD. So I remarked that two sections of a line bundle differ by a meromorphic function. So now given any F inside this OD of U that I just defined, I can send it to F times SD. F times SD is now a section of LD over the open set U. So, and what is happening is just by note that by definition of F being an element of OD of U, F times SD has no poles on U and hence defines a holomorphic section of LD, because the sort of zeros of F cancel all the negative coefficients in D. So when you take F times SD, you get an effective divisor. The divisor of F times SD is an effective divisor. So F times SD defines a holomorphic section of this line bundle LD. So conversely, if sigma is a holomorphic section of LD, we can write sigma as F times SD for some meromorphic function F. Then F automatically satisfies the defining condition of functions in OD of U. For the same reason as I explained, F times SD has to be holomorphic. So F has to satisfy the condition that the divisor of F plus D is greater than or equal to 0. Right? So thus we have a very explicit description of sections of any holomorphic line bundle if we know the divisor associated to it. Yeah, this is the key point is what I have said in the at the end of the sort of 5-6 lines from below. For any divisor D, we define the sheaf OD of U to be this. This is this is how the sections of any line bundle look. Sections of LD look. Okay. So now, thus we have an explicit description of sections of any holomorphic line bundle if we know the divisor associated to it. And now if D1 and D2 are two divisors on X, and D2 minus D1 is a principal divisor, say divisor of some G, then we get an isomorphism of sheaves OD1 of U to OD2 of U given by S goes to G times S. Hence the isomorphism class of the sheaf OD and hence the vector space H upper naught of X comma L are independent of the choice of the divisor in each equivalence class in the class group of X. Yeah. This vector space H upper naught of X comma L, which is what we are interested in for Riemann-Roch theorem, this does not depend on the specific choice of the divisor in any equivalence class in the class group. Okay. Yeah. Fine. So now, okay. Sorry, anybody? Some questions?
No.
Okay. Now, the couple of easy observations are in place. So first observation, negative degree line bundles do not admit any global sections. The reason is simple, because if F is a holomorphic section of L corresponding to a divisor D, which is of negative degree, then from the defining condition, divisor of F plus D is greater than or equal to 0, we find that F is forced to have more zeros than poles, counting multiplicity. This is not possible since the degree of divisor of a meromorphic function is 0. For example, just to pick a small example, take the divisor d equal to minus p. Fix any point p and take the divisor minus p. Then what will be the global sections? They will be exactly all meromorphic functions on x which have a 0 of order at least 1 at p. But it's not allowed to have any poles. But such a meromorphic function doesn't exist, which will have a 0 but no pole, does not exist. So there are no holomorphic sections of the line bundle corresponding to the divisor d equal to minus p. And what I said about this divisor d equal to minus p holds more generally for any divisor of negative degree. In general, one can also have positive degree line bundles which don't have global sections. That's also possible. But certainly the negative degree ones don't have global sections. CP1 such examples don't exist. But a line bundle has a global section if and only if it has non-negative degree. But when the genus is higher, you can have examples of non-negative degree which also don't have global sections. Okay, so I'm sort of almost coming to that. So second observation, if X is a compact Riemann surface of genus at least 1, then the divisor P minus Q for distinct points P and Q has no sections. For let F belong to OD of X, then F is forced to have a 0 of order at least 1 at Q and a pole of order at most 1 at P. At Q, it can have a pole 0 of order at least, it has to have a 0 of order at least 1 at Q to cancel the negative sign, and the pole can have order at most 1 at P so that it doesn't become too negative. So that it doesn't become negative at all, in fact. So since the divisor of F always has degree 0, this means that F has 0 of order exactly 1 at Q and a pole of order exactly 1 at P. Well, this means that F defines a degree 1 map to CP1, which is therefore a biholomorphism. This is a contradiction to the condition that the genus is at least 1. So this in particular shows that the divisor P minus Q is not principal. Principal divisors always have global sections, global holomorphic sections. This divisor P minus Q does not. So this is not a principal divisor. Okay. The second observation proves a claim I made in the previous lecture that if genus is positive, the inclusion principal divisors inside degree 0 divisors is strict. So P minus Q is a degree 0 divisor, but it is not principal when the genus is positive. Okay. Now recall that the holomorphic Picard group was isomorphic to S1 to the power 2g direct sum z. Here S1 to the power 2g represents the parameter space for degree 0 line bundles. It's called the Jacobian, and the second map to Z is the degree map. And the Jacobian has much more structure than merely a group. It's an abelian variety, but I won't go into that. So now this sort of answers what Professor Ravi Kulkarni was asking. That if you are on CP1, then from the degree 0 divisors on CP1 you have the map. Sorry, from the divisors on CP1 you have a map to Z, which is the degree map. That map is actually an isomorphism from the class group to Z. So on CP1 there are as many line bundles as there are integers. The degree map is an isomorphism from the Picard group to Z. In other words, on CP1, every degree 0 line bundle is trivial. Equivalently, every divisor of degree 0 is principal. So this is a very nice picture for CP1 and does not work when the genus is positive. Okay, another comment is that the degree is a purely topological number. If L1 and L2 are two holomorphic line bundles which are isomorphic as topological line bundles, then their degrees are equal. So one way to see this is the other description of degree that I gave as integral of the first Chern class. And the first Chern class is purely topological. So this is independent of the holomorphic structure on the line bundle, this number degree. Maybe I can just pause for a minute and take any questions if there are any. These online lectures can go rather fast, so I would like to take small pauses.
Are you going to consider the tangent bundle and the cotangent bundle?
I'm coming to that. I'm coming to that. For the Riemann-Roch theorem, I'm coming to that. Okay, so with all these, so let me now come to a weak form of Riemann-Roch theorem. So with all these definitions in place, we can state a weak form of the Riemann-Roch theorem, which was the original form of the theorem as stated by Riemann, I think 1857. So weak Riemann-Roch theorem. So for any holomorphic line bundle L over X, dimension of H upper naught of X comma L is bigger than or equal to degree of L plus 1 minus the genus. This is a weak form of the Riemann-Roch theorem. So already this tells you something nice, that as the degrees go on increasing of the line bundles, the global sections go on increasing. Degree tends to infinity, the global sections also tend to infinity. Even this is not clear to begin with. Okay, so this is yeah. It also tells you something, that if the degree is at least if the degree of the line bundle is at least G, then the line bundle always has a global section. This is the other consequence of Riemann-Roch. Low degree line bundles may not have global sections, but if the degree is at least G, it has a global section. Okay, now to convert the inequality into equality, one has to introduce another line bundle, namely the holomorphic cotangent bundle of X, also called the canonical line bundle, whose sections define the holomorphic one forms on X. Yeah, so now to state a more precise theorem, we need to introduce this line bundle, what's called the canonical line bundle. So canonical line bundle. So let ui comma zi be an open covering of X by coordinate charts. On ui intersection uj, I can write dzi as gij times dzj, where gij is the derivative of zi with respect to zj. So when you have a covering of X by coordinate charts ui zi, then on the intersection each of those coordinates is a function of the other. So zi can be expressed as a function of zj, and zj can be expressed as a function of zi. So I define gij to be the derivative of dzi with respect to dzj. Note that Zi and Zj are holomorphic functions of each other on Ui intersection Uj. Now by chain rule, it follows immediately that the collection Gij for every I, j with Ui intersection Uj non-empty defines a collection of transition functions satisfying cocycle conditions. This is just consequence of the chain rule that Gij's satisfy cocycle condition. Now the associated line bundle is called the canonical line bundle, denoted Kx. And a divisor corresponding to this line bundle will be called a canonical divisor. Okay, so this line bundle will play an important role. Okay, now before I go ahead, I want to make one more comment. So the genus of a compact Riemann surface can now be defined alternately as the dimension of h upper naught of x comma kx. Take the line bundle kx, the dimension of space of its global sections. I've commented last lecture, there is always a finite dimensional vector space. So its dimension is called its dimension gives an alternate definition of the genus. Now this follows from the Hodge decomposition. The h upper 1 x comma c is h upper naught of x comma kx, direct sum h upper 1 x comma o. O is the sheaf of holomorphic functions, which is therefore also the sheaf of sections of the trivial line bundle. So you have this Hodge decomposition, so one of the most important theorems in complex geometry. So the left hand side is the left hand side of this equation is the first singular cohomology group with c coefficients. Now by standard algebraic topology, dimension of h upper 1 x comma c is equal to 2g. Right? So this is easy to prove. Now the two vector spaces on the right hand side are conjugate subspaces of h upper 1 x comma c, and hence they have the same dimension. So therefore each of them, so dimension of h upper naught of x comma kx, this is equal to g. So both are g dimensional spaces, and therefore we have established the equivalence of the two definitions. The topological genus is equal to the genus defined this way. So it's defined using a holomorphic object which is kx, but in the end the dimension of the global sections do not depend on the holomorphic structure on x. It's purely topological. A priori it's not clear that this is topological, but okay. So now with all this and these definitions and observations, we can state the more precise form of Riemann-Roch theorem. So theorem: for any holomorphic line bundle XL on a compact Riemann surface X, dimension of h upper naught of x comma L minus dimension of h upper naught of x comma kx tensor L inverse. L inverse means L dual. Inverse is the same as dual for the Picard-group, is equal to degree of L plus 1 minus genus. Yeah, so the previous inequality is now converted into a precise equality. This is the, yeah. Okay. So now I have sketched a proof of this theorem at the end, which I shall discuss if time permits. The proof assumes some basics of sheaf homology. I was told by the organizer not to spend too much time on proofs, so I'll postpone the proof at the end and spend and discuss it in as much detail as I can, depending on how much time is left. So note that this theorem is remarkable because a priori the left hand side depends on the holomorphic structure on L, but the right hand side does not. In fact, both h upper naught x comma L and h upper naught of x comma kx tensor L inverse depend on the holomorphic structure on L, but the difference does not. Yeah, I hope any questions. Okay, so this is now one can generalize this theorem to higher rank. For a holomorphic vector bundle E over X, the Riemann-Roch theorem states that sorry, one little thing. So h up. So I sort of, there's a small issue. This little h upper naught represents the dimension of h upper naught. So I made this comment sometime later. I should have made it at this point actually. So the Riemann, anyway, let me state the Riemann-Roch theorem. Little h upper naught x comma e minus little h upper naught of x comma kx tensor e dual. This is equal to degree of e plus rank times 1 minus genus, where degree of e is defined as the degree of the top exterior power of e. Yeah, if E has rank n, take the nth exterior of E. That defines a holomorphic line bundle, and the degree of that is the degree of E. So it's like the theorem is like the previous one, but the 1 minus G is replaced by rank of E times 1 minus G. And this little h upper naught is just dimension of capital H upper naught. The standard notation. So earlier we had dimension h upper naught minus dimension h upper is degree plus 1 minus genus. Now it's degree plus rank times 1 minus genus. This is not difficult to prove. Main point is to argue that every holomorphic line vector bundle on X has a line subbundle. Using that, one can induct. Okay. Another application of Riemann-Roch theorem is that we now know the degree of the canonical bundle as 2G minus 2. G is the genus of X. Why is that? Now choose L equal to Kx in the above theorem. Above theorem is the Riemann-Roch for line bundles, and we get h upper naught of x comma kx minus h upper naught of x comma o is degree of kx plus 1 minus genus. But now the left hand side is g minus 1, because h upper naught of x comma kx I explained using Hodge decomposition that is equal to g. H upper naught of x comma o, this is just one dimensional because these are the global holomorphic functions on x, so that's one dimensional. So the left hand side becomes g minus 1 dimensional, and so degree of kx becomes 2g minus 2. Note that for g equal to 1, x has a group structure, and so kx is trivial. Using the group structure on the elliptic curve, you can prove the holomorphic cotangent bundle becomes trivial. Therefore, its degree should be 0, which is consistent with this. When put G equal to 1, you get 0 in the degree. So not only is it degree 0, but it's actually the trivial line bundle. Okay. Another nice application is that every compact Riemann surface admits a non-constant meromorphic function. So consider the divisor D equal to G plus 1 times P on X. G is always the genus. Then Riemann-Roch theorem tells you that H upper naught of D is at least two-dimensional, because the right hand side will be degree plus 1 minus genus. Degree is G plus 1. So G plus 1 plus 1 minus G. So the dimension of H upper naught will be at least 2. Yeah, I'm fixing any point P and taking the divisor P plus 1 times G. G plus 1 times P. So this is a two-dimensional vector space, and therefore the constant functions form a one-dimensional vector subspace of this vector space. And this shows that there exists a non-constant meromorphic function on X which lies in this vector space H upper naught G plus 1 times P.
Can you go back to the previous slide?
Sorry?
Can you go back to the previous slide?
This one?
Yeah. So if X has a group structure, then why Kx is trivial?
Well, what happens is, see, at the identity element, you can fix a covector, right? And if you take any element of the group, any element of the elliptic curve, multiplication by that element is a biholomorphism of the elliptic curve, which takes identity to G. If I take the multiplication map by take some point P and take the multiplication map by this element P, so translate everything by P, then the identity element will go to the element P. So this covector at identity will go to the covector at P. So just by translating, you get a nowhere vanishing section, and nowhere vanishing section implies the line bundle is trivial.
Yeah, okay, thanks.
Yeah, so that's a more general fact. Whenever you have a group structure on something, and the group structure is also algebraic, it should not just be some topological group structure. The group structure is algebraic. That means multiplication by an element defines a biholomorphism. Then the tangent bundle or the cotangent bundle are all trivial. Okay, so this is the third. Now another important application of Riemann, very important application of Riemann-Roch is the projective embedding. So one of the most striking applications of the Riemann-Roch theorem is the fact that any compact Riemann surface can be embedded in CPN as a closed complex submanifold for some n. So every compact Riemann surface embeds as a complex submanifold of CPN. So how does one prove that? So here it's convenient to think of CPN as the space of one-dimensional quotients of Cn plus 1 rather than lines inside Cn plus 1. Just a matter of convenience, think of CPN as quotients rather than lines. I will convey the idea without getting into details. So choose a line bundle L over X of degree at least 2G plus 1. Now one can show that this line bundle has the property that given any point P, there exists a holomorphic section S, so that S of P is not equal to 0. This already uses Riemann-Roch, that given a point, you can find a section which is non-vanishing at that point. This allows us to define a holomorphic map from X to this projective space of H upper naught of X comma L. H upper naught of X comma L is a finite dimensional vector space. Take the projectivization of that, and you get we can define a holomorphic map from X to this projective space as follows. Projective space thought of as quotients. Send every point. So I want to now explain how this map is defined. So send every point P to the evaluation map H upper naught of X comma L to L to the fiber over P. LP denotes the fiber of the line bundle over the point P. So this LP is this one dimensional vector space over P. So from H upper naught of X comma L, you have a map to LP, just sending any section S to S evaluated at P. Yeah, sections are evaluated on fibers. Now this is a surjection as stated before, because there is a section which is non-zero at P. So this is a surjective map. Any non-zero map from a vector space to a one-dimensional vector space is surjective. Non-zero is same as surjective here. So this is a surjective map, and therefore defines an element in the projectivization of H upper naught of X comma L. This is the map X to projectivization H upper naught X comma L we have defined. Then again, using Riemann-Roch theorem, one shows that this map is a closed holomorphic embedding. Yeah. So just send every point P to the one-dimensional quotient of H upper naught of X comma L defined by S goes to S evaluated at P. This is the map. Then when one has to prove that this is a closed embedding, which means one has to prove two things: that this separates points, different points go to different points, its map is injective, and the fact that this map separates tangent vectors. That means it is differentially injective. So that is enough to prove that it's an embedding. Now a theorem of Chow then states that any closed complex submanifold of Pn, Cpn, is automatically a non-singular projective variety. That is, it is given by vanishing of homogeneous polynomials. So two things. First, using Riemann-Roch theorem, you prove that X can be embedded inside some projective space. Once it is embedded inside that projective space, Chow's theorem tells you that it's automatically defined by vanishing of homogeneous polynomials. So the upshot of both the things is that every compact Riemann surface can be thought of as a non-singular projective curve. Thus, all compact Riemann surfaces are objects in algebraic geometry, and this allows us to mix techniques from algebraic geometry and complex geometry to study these objects and various other objects defined on them, vector bundles, for example. So yeah, so this makes the subject rich, this mix of algebraic geometry and complex geometry to study Riemann surfaces and things like vector bundles on the Riemann surfaces. Proving, for instance, that the vector bundles admit nice metrics and all such things. Okay, so actually one can show that any compact Riemann surfaces embeds inside P3. P3 means CP3 always, and it embeds inside P2 as a degree D curve only if its genus is D-1 choose 2. So first you embed it inside some large Pn, and then by taking suitable projections, you can actually show that it embeds inside CP3. The proof is similar to the proof of the Whitney embedding theorem in differential topology. So finally, every compact Riemann surface embeds in CP3, and embedding it inside CP2 is more rare. It happens only if the genus is D-1 choose 2. Not if and only if, just only if. So for example, if you take a genus 2 curve, it cannot embed inside CP2 because the genus is not of the form 2 is not of the form something choose 2. Yeah, any doubts? Any questions? Let me pause for a minute and take any questions. Okay. Now let me just briefly mention connections with modular forms. Um, Unfortunately, I don't know number theory, but let me make some comment here because this may be of interest to people. So let X be a compact Riemann surface of genus at least 2. Then the universal cover of X is the upper half plane H, and hence X can be viewed as a quotient H mod gamma for some discrete subgroup gamma in PSL2R. Now you consider the line bundle Kx to the power n. Take Kx tensor Kx n times. That defines a line bundle on holomorphic line bundle on X. Now its pullback to the upper half plane defines a holomorphic line bundle on the upper half plane. Right? You can pull back line bundles. I did not explain this, but in general, if you have a map y to x, and on x you have if you have a line bundle, you can pull back the line bundle to y. How do you do that? You simply take the fibered product y cross L over x. The fibered product is a line bundle. So you pull back the line bundle to the upper half plane, and that's a trivial line bundle. So the pullback, in particular, the pullback of kx to the n to the upper half plane is trivial. Now, if S is a section of kx to the power n on x, its pullback defines a section of the trivial line bundle on h, and hence defines a holomorphic function on the upper half plane. This function satisfies an equivariance property that f of ABCD times z is Cz plus d to the power 2n times f, and defines a weight n modular form. Thus, modular forms can be thought of as sections of powers of the canonical line bundle on compact Riemann surfaces. Yeah, pull back the powers of the canonical bundle on X to the upper half plane. There you can think of it as a function, and the function satisfies a nice equivariance property. Defining a modular form. Yeah. The crucial fact here is that holomorphic line bundles on the upper half plane are always trivial. Okay. Now, okay, I still I have around, let us say, 8-9 minutes. Is that correct?
Yeah, 10 minutes you can take.
Okay, I can take 10 minutes. Okay, 10, that's very good. That allows me to sketch a proof of the Riemann-Roch theorem. Now, first, so this is the Riemann-Roch theorem that I stated before. Now, I'll sketch a proof of this theorem, assuming some basics of sheaf cohomology. This part is a bit technical, so I'll be brief. So, one first proves an easier version of Riemann-Roch theorem. So, this is often called the easy Riemann-Roch theorem, which is the dimension of h upper naught xl minus dimension of h upper 1 x comma l is degree of L plus 1 minus genus. So h upper 1 x comma L denotes the first cohomology group with coefficients in L, first sheaf cohomology group. Now for notational convenience, we denote h upper I x comma f with little h upper I x comma f. So this comment should have come before actually. Anyway, now the first observation is that for the trivial line bundle, this theorem is obvious. Because the left hand side becomes 1 minus g, because L can be taught, instead of L I take the structure sheaf O, and h upper naught of x comma O is just a global holomorphic function, so that's one dimensional. H upper 1 x comma O is g dimensional, as I explained before when I discussed Hodge decomposition. So the left hand side is 1 minus g, and the right hand side is also 1 minus g, because when you take the trivial line bundle, its degree is 0, so the right hand side is also 1 minus g. So this easy Riemann-Roch theorem is very easy if the line bundle happens to be the trivial line bundle. Now we have to induct suitably. For any divisor D and any point P, there exists a short exact sequence of sheaves 0 to O of D to O of D plus P to CP to 0, where the sheaf C suffix P is called the skyscraper sheaf at P, and it's defined as CP over an open set U is just C, the complex numbers, if P belongs to U, and CP of U is equal to 0 otherwise. So if P belongs to U, you would define it to be define it to be C, the group C, otherwise define it to be 0. Thus C suffix P is a sheaf which is supported over the point P. Now the morphism O of D plus P to C suffix P is defined as, if U is an open set not containing P, simply define alpha to be identically 0 on U. Case 2, if P does belong to U and F is a meromorphic function in O of T plus P over U, let N be the coefficient of P in D. Then if F is equal to summation aiz to the power I from minus n minus 1 to infinity with respect to a coordinate neighborhood of P, define alpha of F to be A of minus n minus 1. So you expand F around P as F is a meromorphic function, you expand around P in a coordinate neighborhood. Then the negative power can go only as far as minus n minus 1, and look at that corresponding coefficient A minus n minus 1. Define alpha of F to be A minus n minus 1. Okay, so this is the map alpha, which is the homomorphism of sheaves from O of D plus P to C suffix P. It is now easy to see that in either case the kernel of alpha is exactly the sheaf O of D. So this is very straightforward checking, and therefore this shows that you have this short exact sequence. Now the corresponding long exact sequence in cohomology gives 0 to h upper naught of LD. I'm suppressing the x. It should be x comma LD, but it's just annoying to put x everywhere. X is understood. So 0 to h upper naught of LD to h upper naught of LD plus P to h upper naught of the skyscraper sheaf to h upper 1 of LD to h upper 1 of LD plus P to h upper 1 of the skyscraper to 0. There is actually it makes sense to define the second cohomology group. So the last term will actually be the second cohomology group of LD, but that's always 0. For any line bundle, the second cohomology is 0. So you get the 6-term long exact sequence. Now it follows from check cohomology that the dimension of this h upper naught of CP is 1 and h upper 1 is 0. So this is a very this is an immediate consequence of using check cohomology. Also, degree of LD plus P is degree of LD plus 1. So you have added extra point, so degree increases by 1. Applying all this together, along with the fact that the alternate sum of dimensions of the terms in a long exact sequence is 0, we get h upper naught of LD. Dimension h upper naught LD minus dimension h upper 1 LD is dimension h upper naught LD plus P minus dimension h upper 1 LD plus P minus 1. This is what you get when you use the fact that the alternate sum of dimensions is 0 for this 6-term long exact sequence. Now this shows something interesting. It shows that if the Riemann-Roch theorem holds for the left hand side, if and only if it holds for the right hand side. Yeah, because for example, if the left hand side is degree of D plus 1 minus genus, then then h upper naught of LD plus P minus h upper 1 of LD plus P will be degree of D plus 2 minus genus. So that means degree of D plus 1. That means that is the same as degree of D plus P plus 1 minus genus. So it follows immediately that the Riemann-Roch theorem holds for the divisor T if and only if it holds for the divisor D plus P, and conversely. Now since the easy Riemann-Roch theorem holds for the 0 divisor and every other divisor is obtained from the 0 divisor by adding or subtracting 1 point at a time, it holds for all divisors as well. Right? So you can always go from the 0 divisor to any divisor by adding or subtracting 1 point at a time. We have already said right at the start that the easy Riemann-Roch theorem holds for the 0 divisor. That was this comment at the end. It holds for the trivial line bundle or the equivalently the 0 divisor. So and now by adding or subtracting 1 point at a time, we see that it holds for every divisor. So this completes the proof of the easy Riemann-Roch theorem. And now one proves a duality theorem called Sayre duality, which in this special case states that h upper 1 of x comma L is isomorphic to h upper naught of x comma kx tensor L inverse dual. So basically one defines a non-degenerate pairing from h upper naught of x comma kx tensor L inverse cross h upper 1 x comma L to C. And therefore you get the isomorphism of one vector space with the dual of the other. And that completes the proof of the Riemann-Roch theorem.
Thanks.
So these are two references. One is Compact Riemann Surfaces by Raghavan Narasimhan, Berkhauser publication. And there are some online notes by Pablo, who was a faculty at TIFA for many years, and I've included the link. So these are two very good references on this subject. So I'll stop with that.
These links work?
Yes.
Thank you, Sudarshan. Thanks a lot for this wonderful talk. It was very detailed and very nice talk.
Thanks.
So let's see if there are any questions from the audience. I don't see any questions in the chat box.
If you can say something more on that equivariance modular form slides.
You know, all the modular forms, etc., is out of my depth, frankly. So I only said what I know about it. Yeah. Basically, yeah, you're pulling it back to the upper half plane. So you see there are various points on the upper half plane which are going to the same point on the Riemann surface. So the sections are going to be related in some way. Sections over one point with sections on at some other point, both of which go to the same point on the Riemann surface. So that is the equivariance condition.
Okay.
So Devendra, there is an expository article by Professor Raja Sridharan, okay, from CMI, and he has given a purely number theoretic proof of Riemann-Roch theorem, and it's absolutely I mean, the tricks and the ideas are very nice. I read it when I was doing my PhD. I don't remember it thoroughly, but I would recommend you, if you are interested in, to have a look at it.
So it is number theoretic proof of Riemann-Roch.
Correct. Yeah.
We'll see then.
So, are there questions on the YouTube?
No.
I don't think so.
Okay. So Sudarshan, so let's thank everyone to Sudarshan for this wonderful series of talks, and we hope to have him back sometime later as well. So Sudarshan, I hope you will agree with this.
Yeah, assuming it's something I know.
Of course, yeah. Okay. So thank you very much again.
Yeah, thanks.
Yeah. So we will meet again at 7 o'clock for Nilima's talk on hyperbolic tessellations.
Makaran, can you stop the live stream and change the live stream keys?
Yes, I will.